Going over the review sheet today. Finishing going over the review sheet today. Yep. So what we're doing next is the possible rational zeros, or possible rational solutions. And we put it in the form of plus or minus p over q, where p is the factors of the constant term, and q is the factors of the leading coefficient. So, looking at this here, the factors of the constant term, well, our constant term is going to be what? Constant term is the variable without, or the number without a variable. And our number without a variable in this case is 27. So the first thing we want to do is find the factors of 27. You'd always want to start with 1 in the number itself, so 1 and 27 would be our first set of factors. Then we could go 2 is not a factor, but 3 is, 3 and 9, and then that's going to be it. Those are the only two factors of 27, 1 and 27, 3 and 9. Q is the factors of the leading coefficient, the number in front of the variable without an exponent. So we're looking at the factors of 9, which is going to be 1 and 9, or 3 and 3. Now, even though 3 shows up twice, we're only going to write it once, because any factors that we would have for the first factor of 3 for Q would be the exact same numbers as the second one. They're just going to be repeated. Need one?
Yes.
Room 10? Think you know how to fob in?
Yep.
They should be on the printer by now. I did send 2 copies of it, so. Because once we get all the factors of P and Q, we're going to divide every factor of P by every factor of Q. Now, we could do it one at a time and then do 1 over 1, 1 over 3, 1 over 27, and do it that way. I think it's easier and a lot nicer to make sure we get everything listed if we divide each factor of P by Q one at a time. And I always start with 1. And 1's nice to start with Q, because no matter what our factors of P are, when we divide it by 1, we get that factor back. Because 1 divided by 1 is going to give us 1. 3 divided by 1 is 3. 9 divided by 1 is 9. And 27 divided by 1 is going to be 27. We just get the numbers back. Now, one of the big things I will say with the rational zeros is you definitely need that plus or minus, because that's part of the answer, because we have positive 1 and negative 1. We have positive 3, negative 3. Positive 9, negative 9. Positive 27, negative 27. If you don't put that plus or minus, you're missing half of the solutions, half of the answers for this here. So you're going to lose half the points for this problem if you do not put the plus or minus. So we do need that. Now, from there, we can move on to doing the same thing with 3. So we'd have plus or minus 1 over 3. Now, 1 over 3 does not reduce. That is simplest form as it gets. And it's not repeated, so we do have 1/3. The next one we would have would be 3 over 3. Well, 3 divided by 3 is 1. It's already listed. We don't have to write it again. Then we would do 9 over 3. 9 over 3 reduces to 3. It's already listed. We don't have to write it a second time. And lastly, 27 over 3. 27 divided by 3 is 9. It's already listed. We're done with that one. Now, yes, we could grab a calculator and say 1 over 3 is 1/3. It's not listed. 3 over 3 is 1. 9 over 3 is 3. 27 over 3 is 9. The calculator will simplify them for us. If you need the calculator to help you simplify at this point, use it. Use the tools at your disposal. And then we're going to do this again with 9. Now, 1 over 9 doesn't reduce. It's not been repeated. It is there. I will send it again.
Okay. I was like, why are these cycles?
I have no idea why it printed.
It threw me off guard because I was like, are these cycles?
Yep. I have no idea why it's freaking out. Because it's not that it printed it sideways.
Yeah.
It literally thought it was.
Oh, what the heck? What the heck?
Yeah, if it wasn't for the fact that it showed me the shot, that is. Yeah. I have no idea why it was set to whatever that was. Yep. There we go. That's better. Those are garbage. Okay. So we had plus or minus 1 over 9. That's it. Now 3 over 9 is 1/3. We already have it. 9 over 9 is 1. 27 over 9 is 3. So really the only one that was added to it is 1/9. Now since we're out of factors of q, we're done. So the rational zeros for this here is positive, negative, plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27, plus or minus 1/3, and plus or minus 1/9. And those would be all of our rational zeros. Questions on rational zeros? Do we feel good with rational zeros? Okay. Descartes' rule of signs. We want to use this to find the number of possible positive, negative, and complex zeros. We're going to look at number 28 for this one here. Now, to find the possible number of positive zeros, we have to count the number of sign changes of the function itself. So as we go from x to the 7th to x to the 5th, it goes from positive to negative, so that would be 1. X to the 5th to x to the 4th, it goes from negative to positive, so that would be 2. X to the 4th to x cubed would be 3, positive to negative. Then we go from negative to negative, so we don't count it. Negative to positive would be 4. Positive to negative would be 5. So the number of positive solutions we can have is 5 or less than it by an even amount, because according to Descartes' rule of signs, the number of positive zeros is equal to the number of sign changes from term to term or less than it by an even amount. Smallest even number we can have is 2. So it could be 5, 3, or 1. Now we can list all of those out so that we know that, but that is not part of our final answer. Now to find the number of negative solutions, possible number of negative solutions, we need to plug in negative x in every x in g of x. And the main way we would do that, or what we would go about doing for this here, is looking at the exponent, that power. If the exponent's still not doing it,
The machine's restarting and it's only at 12
the max number is, who knows?
Yeah, it was like restart. It said error, and so it said restart. So I pushed the restart button, and then I stood there, and it just kicked on.
Yep. Nope. There's no telling what's causing the error this time. It has issues. Remind me before the end. I will get you a copy of this.
You have the reference posted.
Yep. Have the full review too. Now the full review is almost 2 hours. You don't have to watch the whole thing, but it does go through everything. So now to find g of negative x, we're really plugging in negative x in every place where there's an x. Now the way I look at it is I take each term. Now the first one we're looking at is 6x to the 7th. If that exponent's odd, we change the sign. If that exponent is even, we leave it alone. Because negative x to the 7th power, that negative would come out, which would make that 6 go from positive to negative, because we're applying that negative from x to the 7th, negative x to the 7th. Now our next term in this case is 5x to the 5th. If we multiply a negative x by itself 5 times, it would still be negative, and that negative with the negative 5 would turn it from negative to positive. Our next term is 27x to the 4th. Because it's a 4th power, that power is even, means we need to keep the sign the same. We need to leave it alone. Because negative x to the 4th would just be positive x to the 4th, even number of times. So since 27 is positive, it's going to stay positive. If that 27x to the 4th had been negative, it'd still be negative. We don't do anything to the sign. Our next term is 30x cubed. X to the 3rd power, that 3rd power is odd, so we need to change it from negative to positive. When the exponent's odd, change the sign. When the exponent's even, leave it alone. Our 20x squared is even. It's an even exponent, so the sign would stay the same. Our next term is 5x. Now, even though it's not written, the exponent's understood to be 1. 1 is odd, so we'd have to change it from positive to negative. And we don't do anything to our constant term, because our constant term does not have a variable for us to plug in. And once we finish doing this, we'll count the number of sign changes. Our first one's from negative to positive, so that'd be 1. Positive to positive, we don't count it. Positive to positive, we don't count it. Now positive to negative would be our second sign change. Negative to negative, negative to negative. So for our negatives, the number of sign changes we had was 2, telling us we have 2 negative zeros, or less than it by an even amount. Well, 2, we can subtract 2 from it, an even amount from it, again, 0. Now, we need to figure out all the arrangements of our positive and negatives and look at the degree to help us come up with the complex. So one of the ways we could do this, as we listed out, we have 5 and 2, 5 and 0, 3 and 2, 3 and 0, 1 and 2, 1 and 0 is one way to go through this and making sure that we have all possible combinations of our positives and negatives. The way that I look at it is I take the most of each. The most positives we could possibly have is 5, yes? And the possible number of negatives that we can have is 2. That's the most positives and most negatives we can have. And if I do have 5 positives and 2 negatives, we have a total of 7 solutions, yes? Now the degree of the polynomial function is 7 also, yes? Since the degree is 7, it tells us we should have 7 solutions. And if we do have 5 positives and 2 negatives, we do have all 7, which tells me that the number of complex has to be 0. Because if I have 5 positives and 2 negatives, We have all 7 solutions. There are no complex solutions. Now at this point here, I subtract 2 from the negatives, take away those groups of 2 from the negatives till I can't. Because I can do 2 minus 2. If I take away 2 negative solutions, it is still possible we could have 5 positives and 0 negatives. But we need 7 solutions. And if I only have 5 positives and 0 negatives, we're missing 2. So those 2 solutions have to be complex. Can we take any more groups of 2 from the negative? No, because we would have negative 2 negatives. We can't have a negative number of solutions. So what we do is see if we can take a group of 2 from the positives. And we can. We can go from 5 to 3. Reset the negatives back to the maximum number we can have, which is 2. So our next setup says that we can have 3 positives and 2 negatives, which does give us a total of 5 solutions. We need it to be 7, so that means those other 2, those missing 2 solutions have to be complex. Well, now we repeat the process again. I could have 3 positives and 0 negatives. Total number of solutions that we have right now is 3. We need 7, so I'm missing 4. Those 4 are complex. I can't take any more groups from the negatives, but I can take one more group of 2 away from the positives, telling me that I can have 1 positive, 2 negative, and 4 complex. Or lastly, we could have 1 positive, 0 negative, and 6 complex. So really, we've put every group, our 5, 3, and 1 for positive with every arrangement of the negative, 0, and 2, and the complex tells us how many are missing out of the total number. So this is our total arrangement of all possible positive, 0, and complex solutions we could have for this polynomial function. Also, the complex values are always going to be even or 0. We're going to have an even grouping of them. They're all going to be divisible by 2. So it's always going to be even. Questions on this here? Solving polynomial functions. The first thing I would do for any of these here is graph it. I would graph the thing. Because if we look at 29, the degree is 5. So the number of solutions we should have for this is 5. When we finish this out, we'll have 5 solutions. Now we want to find n minus 2 solutions from graphing or by any method. Since the degree is 5, 5 minus 2 is 3. Because if I find 3, we can get it to a quadratic. We can solve from there. If I get 4, we get it down to a linear, where the only variable we have is x to the first power. That's even nicer. Best case scenario, the absolute one that we want is that it tells us 5. If it tells us all 5 solutions, we are done because the degree is 5. There should be 5 solutions. So the first thing I would do is grab the graphing calculator and tell it x to the 5th minus 20 x to the 3rd plus 20 x squared minus 21x plus 20. Graph. And we see here it crosses the x-axis in 3 spots. Now, I would use the graph to kind of give us an idea of where the solutions are. We don't know where the table is going to be set, because it could be high in the negatives or low in the positives. But if I look at this here, I see one's around -5, somewhere in that location. That's where that x is. I see we have one close to 1 and possibly close to 4. That's where it's crossing the x-axis. So when I look at the table, I know to look somewhere near -5. Actually, it is -5. And then at 1 and 4, we do have those zeros. It gives me an idea of where to look. where I need to scroll up or down if it's not showing me. So negative 5, 1, and 4. Now, according to our graph, it does have an odd multiplicity at all three spots. So it's going to show up 1, 3, 5, not 5, but 1 or 3 possibly based off the degree. But most likely that's not going to happen. That would mean negative 5 has to show up 2 more times, or 1 or 4. Now let's put our numbers across the top. Now we have 1 for x to the 5th. What's our x to the 4th value? Is there an x to the 4th? No, so that number has to be 0. We do have an x cubed term, so its number is negative 20. X squared is positive 20. X is negative 21, and our constant term is 20. If we have a term missing, we have to fill it in as 0. We would not consider x to the 6th. Even though there is no x to the 6th term, we would not fill a number in for it. Because the biggest term listed is x to the 5th. We're looking from x to the 5th down. We wouldn't go up past it. So we need to figure out which one we wanted to use first, 1, 4, or negative 5. Negative 5, let's go there. Now at this point here, we'll do our synthetic division. So we do negative 5 times our 1, which would be negative 5. At this point, we would add the 2 together. 0 plus negative 5 is negative 5. Now, negative 5 times our negative 5 is going to be positive 25. Then we would add the 2. So negative 20 plus 25 is going to be 5. Negative 5 times positive 5 is going to be negative 25. And 20 plus negative 25 is, well, negative 5. Negative 5 times our negative 5 is not going to be negative 25. What will that be? Positive 25. Negative 21 plus 25 is 4. Negative 5 times positive 4 is negative 20. And 20 plus negative 20 is indeed 0. Which number do we want to do next, 1 or 4? 4. Now, as we do this here, we'll repeat the process. 4 times 1 is 4. Negative 5 plus 4 is negative 1. 4 times negative 1 is negative 4. 5 plus negative 4 is 1. 4 times positive 1 is positive 4. And negative 5 plus 4 would be negative 1. And lastly, 4 times negative 1 is negative 4, and 4 plus negative 4 is indeed 0, yes? Well, that's what we expected because the graphing calculator already told me that 4 is a solution. Now, even though 4, negative 5, or 1 could be repeated, I would still do all of them once. I wouldn't do any of these repeated just in case it doesn't happen to be a repeated solution for these here, because it is going to take us down to a quadratic. 1 times 1 is 1. Negative 1 plus 1 is 0. Our 1 times 0 is 0. 1 plus 0 is 1. 1 times 1 is 1. Negative 1 plus 1 is 0. So we get 1, 0, 1 as the numbers left over, yes? Now at this point here, we could try positive 1 again. It won't work. It would actually give us a remainder of 2. 4 and 5 also aren't going to work. But the nice thing about this here is if we put the remainder, or put our variables back in, last number is our remainder, our 1 is our term without x, 0 is our term with x squared, telling me that my final expression, the final equation we have is x squared plus 1. So since the middle term is 0x, we don't have to list it, giving us this here. Now, part of the reason I say this is nice, we don't want to try the others as well. Do we have a middle term? No, we can still use quadratic formula completing the square, but I would rather use square root method, because if we don't have a middle term, get that squared term by itself, because we can subtract 1 from both sides, telling me x squared is equal to -1, yes? And since the squared term is by itself, we can square root both sides. The square root of x squared is x is equal to plus or minus. Now we need to figure out what the square root of -1 is. Well, there's 2 ways to go about it. One, I know that this negative is going to have to come out as I, yes? What's left over? The square root of 1. And what is the square root of 1? 1. So really we're looking at this plus or minus 1i, or just plus or minus I. But what is I by definition? I by definition is the square root of -1, yes? So the other way is square root of -1 is just I. That's just by definition. So the last 2 solutions are positive, negative, I. So our 5 solutions are -5, 1, 4, positive I, and negative I. So we have positive I, negative I, that's 2, and then the 3 we started with. So that does give us all 5. Questions on this here? Yeah. I will tell you this, you do not need the quadratic formula or completing the square for any of the problems on the test. If we have to actually solve for a quadratic on the test, I made it so that every single one can be done by completing or square root method, just to make it a little bit nicer on y'all. Huh? Yes. Yes. Mm-hmm. And, mm-hmm. So I just need all the work by the end of the week. If you can get it to me before then, that would be great. Since the week before Thanksgiving, those matrices, so the GB4, the GB assignments, Green Book assignments, and then Chapter 4. So really, if it has Chapter 4 or 4 point something attached to it, it's due. Yep. Questions on this here? We're going to skip, we'll look at 30. X to the 4th minus 6x cubed plus 7x squared plus 6x minus 8. Now, before I graph this here is a degree what? 4, yes? Since the degree is 4, we should have how many solutions? 4. Now, the minimum number of solutions we need is 2, n minus 2. Degree is 4, so 4 minus 2 would give us 2. And if I graph this here, we do see that it does intersect the x-axis at 4 spots, yes? So as long as those are all nice zeros, that's going to be helpful. Well, when x is -1, the y value is 0. That's a solution. When x is 1, the y value is 0. When x is 2, the y value is 0. When x is 4, the y value is 0. We're looking for what values of x will make the y value be 0. We do not care about what value of y will make the x value be 0. That really doesn't tell us anything. The fact that when x is 0, y is negative 8 means nothing. Our negative 1, 1, 2, 4, we have 4 values of x that make this function equal 0. And they are negative 1, 1, 2, 4, yes? How many solutions should we have? 4. How many do we have? 4, yes? Are there any other solutions that we need? No. We're done. It gave us all 4. Now, especially before the fundamental theorem of algebra, before we went over the fact that the degree is equal to the number of solutions, we would still do synthetic division to verify that, yes, these are all the solutions. But now that I know that the degree is equal to the number of solutions, degree is 4, there's 4 solutions, we have 4 values of x that make this equal 0, we're done. We know that's everything. Questions on 30? You know what? Let's look at 31. Not 31, 32. 9m to the 5th minus 27m to the 3rd. This is kind of easy to graph because there's only 2 terms. We graph it. We see that we do hit 2 numbers that are close to 2 and negative 2. And then it does this weird downward S through the origin. So that tells us one of the zeros is 0, yes? It doesn't give us any others. So what we can say for certain is that m is equal to 0, yes? Funny enough, if there is no constant term, if there's no term without a variable, 0 is always a solution. If the equation only has variable terms, 0 is a solution, and it repeats equal to the smallest exponent attached to a variable. Tells us how many times it repeats. So m to the 3rd is our variable with the smallest exponent. So it actually told me 0 is a solution 3 times. We won't necessarily have one like this on the test, but it's really telling me 0 is going to be a solution 3 times. Because really we can factor out m to the 3rd, which is going to give us actually 9m cubed. We can factor it out, leaving us with m squared minus 27. But if we start off with 0, 0 times 9 is 0. Well, 0 plus 0 is 0. 0 times 0 is 0. Negative 27 plus 0 is negative 27. 0 times negative 27 is 0. 0 plus 0 is 0. 0, 0, 0, 0. Now, I really blew through the last few because it's just zeros and adding and multiplying by 0. Well, let's try it again. 0 times 9 is 0. 0 plus 0 is, well, 0. 0 times 0 is 0. 0 plus negative 27 is negative 27. 0 times negative 27 is 0. 0 plus 0 is 0. 0 times 0 is 0. And 0 plus 0 is, lo and behold, 0. We'll do it one more time. 0 times 9 is 0. 0 plus 0 is 0. 0 times 0 is 0. Negative 27 plus 0 is negative 27. 0 times negative 27 is 0, and 0 plus 0 is 0. Now, we can't do it again because the main reason we could do it was those last three numbers, last two numbers, last number were all 0. Here, we won't get that because that negative 27 is going to come down. But if we do fill the variables back in, remainder, constant, x squared is telling me that I have x squared minus 27 is equal to 0. No middle term, so square root method. Add 27 to both sides. Tell me that 9x squared is equal to 27. Divide both sides by 9, telling me x squared is equal to 3. And lastly, square root both sides, tell me x is equal to plus or minus the square root of 3. So our solutions for this are 0, 0, 0, positive square root of 3, and negative square root of 3. So we do have 5 solutions. It just works out that 0 is a solution 3 times. Yes. Partially because I'm missing an m squared m in constant term, so it has to be that. The other way we could do this is greatest common factor between these three is 9m cubed, because 9 is divisible by both 9 and 27. I do have 3 m's in common with both. And if I factor it out, I'm left with 9m cubed times m squared minus 3, yes? Well, whenever we have 2 or more things multiplied together to equal 0, one of them has to be 0. M to the third is just saying that I have m times itself 3 times. So for m to the third, each one of those values of m could be 0. So really we have that there. And then we could say m squared minus 3 is equal to 0. Kind of solve it out. Or really just from us and just deduction, I don't have a constant term, so I can plug 0 in as a solution. And it works out the least degree, or the smallest exponent attached to the variable, will tell us how many times 0 is a solution. So if we had an m squared term also, it would just tell me 0 is a solution twice because of the m squared, because I can factor it out. It's one of those oddity ones. It's interesting, but that's about it. Any other questions on this here? Okay, we'll stop there. Your first part of your test is to